New frontiers in engineering are explored, focusing on the unique challenges of designing for extraterrestrial environments. Viewers are offered a captivating glimpse into the innovative solutions being developed for humanity's expansion beyond Earth. Humans can live in space, but it requires specialized technology and environments to mitigate the dangers of space. While humans can survive for short periods in space with proper equipment like spacesuits, long-term habitation presents numerous challenges related to radiation, lack of atmosphere, microgravity, and psychological factors. It is possible to create an artificial atmosphere in space, although it presents significant engineering challenges. This can be achieved by enclosing a space, like a lunar base or a space station, and filling it with breathable air, maintaining the necessary pressure, temperature, and gas composition. Radiation and extreme temperatures in space can significantly shorten lifespan by causing cellular damage and impacting various bodily systems. Radiation can damage DNA and lead to increased cancer risk, while extreme temperatures can cause thermal stress and disrupt bodily functions. Energetic particles in space radiation can penetrate the skin and damage DNA, increasing the risk of cancer and other health problems. Radiation exposure can hinder neurogenesis, the process of generating new brain cells, and potentially lead to degenerative diseases of the central nervous system. The extreme temperature variations in space, very hot during the day and very cold at night, can cause thermal stress on the body, disrupting normal physiological functions. The absence of gravity in space also affects the human body, leading to muscle atrophy and bone loss, which can contribute to overall health decline. Global challenges like the climate crisis, water scarcity, and food security necessitate a fundamental reevaluation of terrestrial engineering practices. Traditional approaches are often unsustainable and exacerbate these problems. A rethink requires focusing on renewable energy, sustainable infrastructure, and resource management to create a more resilient and equitable future. Engineering practices, particularly in construction and transportation, contribute significantly to greenhouse gas emissions. Rising temperatures and extreme weather events demand a shift towards low-carbon solutions. Focus on energy-efficient buildings, sustainable transportation systems, public transit, cycling infrastructure, and carbon capture technologies. Developing infrastructure that can withstand more extreme weather events is also crucial. Implement water-wise technologies like smart irrigation, rainwater harvesting, and wastewater treatment and reuse. Microgravity and lunar/Martian gravity environments present numerous engineering challenges for long-duration space missions. These include issues related to fluid behavior, material handling, structural integrity, human physiology, and resource management. These challenges require innovative solutions in areas like in-space manufacturing, life support systems, and radiation shielding. In microgravity, fluids don't behave as they do on Earth. Liquids can levitate, making fluid transfer and containment difficult. This impacts life support systems, propellant management, and even fire safety, where smoke behaves differently. Microgravity can affect the stability and integrity of structures, especially during construction or assembly. While not as extreme as microgravity, lunar, 1/6 Earth's gravity, and Martian, 3/8 Earth's gravity, gravity still impact human physiology and require specific countermeasures. Gravity is fundamental to space engineering, influencing everything from spacecraft design and trajectory planning to the very formation of celestial bodies. It dictates how spacecraft move, how they are launched and landed, and even how they are constructed to withstand the forces of space. Gravity is a key factor in determining the trajectory of spacecraft, influencing how they move through space and how much fuel is needed. Spacecraft can use gravity assist maneuvers to change their trajectory and velocity by strategically flying by planets or other massive objects. Understanding escape velocity, the speed needed to break free from a celestial body's gravitational pull, is crucial for launching and landing spacecraft. In long-duration spaceflights, artificial gravity, e.g. through centrifugation, is being studied to counteract the negative effects of microgravity on astronauts' health. New rocket propulsion techniques are revolutionizing space engineering by enabling faster, more efficient, and more sustainable space travel. These advancements, such as electric propulsion, nuclear thermal propulsion, and rotating detonation rocket engines, offer significant advantages over traditional chemical rockets, paving the way for ambitious missions to Mars and beyond. Systems like ion and Hall-effect thrusters use electric and magnetic fields to accelerate ions, achieving much higher specific impulse efficiency than chemical rockets. This allows for longer missions and reduced propellant mass. In summary, new rocket propulsion techniques are revolutionizing space engineering by offering higher efficiency, faster travel times, and the potential for more ambitious missions. These advancements are crucial for pushing the boundaries of space exploration and enabling future human spaceflight to Mars and beyond. Space-based construction and maintenance robotic technology powered by artificial intelligence allows essential space infrastructure tasks to take place. Robotic construction technologies need to build and fix space structures because long and challenging missions demand them instead of human controls. Robotics and AI are revolutionizing space engineering, enhancing capabilities and efficiency across various aspects of space exploration and infrastructure development. AI assists in data analysis, autonomous navigation, and optimizing mission planning, while robots handle complex tasks, exploration in hazardous environments, and even construction in space. This combination leads to reduced costs, increased safety, and new discoveries, ultimately accelerating humanity's reach into the cosmos. Advanced robotics and AI are increasingly vital in hazardous environments for surveying, construction, and maintenance, offering enhanced safety, efficiency, and precision compared to traditional methods. These technologies minimize human exposure to dangerous conditions, optimize resource allocation, and improve the quality of work in challenging settings. Robots can operate in environments with toxic substances, extreme temperatures, high altitudes, or radiation, eliminating the need for human workers in these hazardous conditions. In conclusion, the integration of robotics and AI into hazardous environments offers a paradigm shift in surveying, construction, and maintenance, enhancing safety, efficiency, and precision while optimizing resource utilization and reducing costs. The future of space exploration and development is poised to be significantly impacted by autonomous swarms and self-assembling structures. These technologies offer potential solutions for constructing large-scale infrastructure in space, exploring distant celestial bodies, and mitigating the challenges of space debris. The future of autonomous swarms and self-assembling structures in space holds immense promise for revolutionizing space exploration, resource utilization, and infrastructure development. Continued research and development in these areas will be critical for unlocking the full potential of these technologies and enabling humanity's expansion into the solar system and beyond. Astronauts undergo rigorous training to prepare for the physical and psychological demands of space travel. This includes learning to use specialized equipment, handling emergencies, and adapting to zero gravity. Ongoing research into areas like radiation shielding, closed-loop life support, and advanced propulsion systems is essential for overcoming the challenges of future space exploration. Long-duration spaceflights expose astronauts to harmful cosmic radiation. Shielding spacecraft and developing methods to repair DNA damage are potential solutions. Overcoming challenges in space requires addressing physical, psychological, and logistical hurdles. These include mitigating the effects of zero gravity, maintaining mental well-being, ensuring life support systems, and managing risks from radiation and long-distance travel. Human expansion into space faces numerous challenges, primarily revolving around the harsh realities of the space environment and the limitations of human physiology. These include radiation exposure, the effects of microgravity on the body, the psychological strain of isolation and confinement, and the immense distances involved. Additionally, the development of sustainable life support systems, resource utilization, and addressing ethical and political considerations are crucial for successful long-term space colonization.